Second addition reaction for alkenes would be the hydration of alkenes. And hydration, as you know, involves water. So we're going to go ahead and add water to an alkene. And I think I'll use a substrate that I used before because it's asymmetric and we'll have two possibilities for the first step. And this one's going to be a little different because essentially it's got to be catalyzed. So if you tried to add water directly to an alkene, it's not a potent enough or reactive enough molecule to get things going, so it just wouldn't work. Water could sit in the presence of an alkene for a very long time and nothing would happen, so it has to be catalyzed. So when we write the overall reaction for this, we'll write like the alkene plus water, and then above the arrow we'll write what the catalyst is. So in this case, we would use sulfuric acid, aqueous sulfuric acid, as the catalyst and sort of the reactant because there's water in there, and that would kick off the first step. So water wouldn't directly react with the alkene, and then what you'd end up with as a product would be an alcohol, and you could get a variety of different constitutional isomers depending on where the OH ends up. So let's look at the mechanism. And the first thing that would happen is we need a strong acid to react with the alkene, and that's why we put the H2SO4 in. And as you should know, when you have H2SO4 and that's in the presence of water, you get an equilibrium set up that's driven fairly towards products because this is a very strong acid. It will protonate the water and make H3O plus, and then the counterion that's left over, the conjugate base of the H2SO4, is the HSO4 minus, the hydrogen sulfate. And this is extremely unreactive. Since it's the conjugate base of a very strong acid, it's not very basic at all. And if you go and study nucleophiles, it's not very nucleophilic at all. So this isn't really going to react with anything. It ends up being pretty much a spectator. So when you throw sulfuric acid into water, you get the potent H3O plus, strong acid, and a spectator counterion. So that makes sulfuric acid a good thing for being an inert electrolyte or a strong acid that won't do anything else to the reactants. So it's often the catalyst of choice for this type of reaction. So when we put our alkene in with aqueous H2SO4, this reagent, the H3O plus, is pretty much what's in there and doing the business. So this being a strong acid, the pi bond of the alkene will grab the H plus of the strong acid. The bonding electrons that were holding the acidic hydrogen to the rest of the molecule that bonding pair is going to become a lone pair. And so when we have this reaction, we get the alkene, and this is exactly like the first step of the other addition reaction we did, the hydrohalogenation, except now we're using a different strong acid. So the alkene is protonated by a strong acid to give a carbocation, and depending on where the hydrogen goes, we're either going to get the primary or the secondary carbocation. So protonation of an alkene to give a carbocation intermediate is the first step in this addition reaction, and that's going to produce some water as a byproduct. So after the H3O plus loses its H plus, you end up with some water. Now the carbocation is very reactive, it's very electrophilic, it's looking for any electrons it can find so that it can react and fill the octet of the carbon, that's the carbocation. So what happens in the next step is that an electron pair in the water we'll go ahead and add the carbocation. And as you can see, we have two different carbocations, the secondary carbocation and the primary carbocation, and either one of these is going to react with the water, which is not a very good nucleophile. Again, I introduced this term in a previous video, but the nucleophile is looking for positive charge, and so water with its pair of electrons can look for positive charge. And then the electrophile, electron lover, the electrophile is looking for electrons, so there we go. The lone pair on the oxygen can go bond to the carbocation and become a shared pair, and that will give us again another intermediate. Now if we have a positively charged ion with a neutral molecule, what we're going to end up getting is a positively charged product, because a positive charge isn't just going to evaporate. And it's very important to watch where the positive charges are. So this guy here, this oxygen, is formally positive. And we'll have the same thing with the other carbocation. The water nucleophile will go and bond to the carbocation carbon. And then you'll get what essentially is called an oxonium. If I remember my terms right, the oxonium is the oxygen with the positive charge. And this is going to, essentially, it looks like a protonated alcohol. So if you had an alcohol and you protonated it, you would get this. So now we're going to have another water molecule come in. So remember, we had a water produced when the H3O plus lost its H plus, but we also have a reactant water molecule that's going to get involved in the reaction. And what this will do is deprotonate the alcohol. So the water will go grab an H plus off of this guy. This bonding pair of electrons will become a lone pair, and that will give us our alcohol that was our target product. Right, so these hydration of alkenes produces alcohols, and the other protonated alcohol or oxonium will also undergo the same type of reaction. The lone pair on the water will go grab an H plus off of the oxonium and leave the OH there. And so you can get two different isomers of propanol. You get the 2-propanol if the secondary carbocation goes on to form product, or you can get 1-propanol, 1-propyl alcohol, so the propyl alcohol. 1-propanol is when the OH ends up on carbon number 1. And that would be if the primary carbocation goes on to form products. And as we learned before, the primary carbocation is less stable and is going to be the minor intermediate, where the secondary carbocation is going to be the major intermediate. So the 1-propanol then is the minor product. The substitution usually goes on the carbon with more carbons on it. And so the 2-propanol is going to be the major isomer. And you'll notice when you add the H plus to the water, you regenerate the catalyst we introduced in the beginning. So both of these will have the H3O plus generated. And since I'm about out of room, I'm just going to write a little minus H3O plus. Say this water grabs the plus and exits as an H3O plus, right? And that regenerates the catalyst that kicked things off. So you have, and it's good to summarize these guys, we have 3 steps in this one. We have the alkene is protonated by the strong acid to give a carbocation intermediate. Then the carbocation intermediate is attacked by the nucleophilic water to create an oxonium intermediate, then the oxonium intermediate is deprotonated to form the alcohol product. So 3 steps for the hydration of alkenes, and it's a little more complicated than the hydrohalogenation because we didn't generate the product after the nucleophile attacks. We had to do a subsequent deprotonation. So I hope this was helpful. And the hydration of alkenes is a very important reaction because alcohols are very valuable commodities.